So chemists often need to know the number of atoms in a sample, and that's because chemical processes happen between atoms. 2 atoms of hydrogen and 1 atom of oxygen combine to form 1 molecule of water. And so we need to know numbers of particles. Well, you can't count them. What do we do with objects in real life that are too numerous to count? Do you go to the store and say, I want 72 pieces of paper, and they count out 72 pieces of paper? No. You can buy a package of 100 sheets of paper, or you can buy a ream, which is 500 sheets of paper. You go to Costco and you buy eggs. You can't buy 17 eggs. You can buy 2 dozen eggs, or you can buy 5 dozen eggs, or then there's some crazy number of eggs. What does a dozen mean? 12. 12 what? 12 whatever you're talking about, right? You can have a dozen bagels, a dozen donuts, now I'm getting hungry, a dozen eggs, a dozen pencils, a dozen planets. You could have a dozen of anything. It's a counting unit, right? So these counting units, a dozen and a gross is 144 objects, or a ream is 500 sheets of paper. Those are useful for everyday things, but they're still too small for counting atoms. So we need a number like this, a unit like this, that's just a much bigger number. Enter the mole. So a mole, sometimes called the chemist's dozen, because it works like a dozen. A dozen is 12 things. A mole is a particular number of things. It's just this really weird number. A mole is 6.02214 times 10 to the 23rd units of that thing. That's a really, really big number. The 14 here, if you remember it, great. If not, 6.022 times 10 to the 23rd is usually good enough. So 1 mole of a substance is 6.022 times 10 to the 23rd particles. That's called Avogadro's number, because sometimes that's easier to say than the whole thing. It's named after the scientist Amadeo Avogadro. A mole is a useful number because it's a useful size. So 22 pennies, the ones that are all copper, 22 copper pennies, that's approximately 1 mole of copper atoms. So, you could hold those in your hand. Nice amount, right? A tablespoon of water is about 1 mole of water molecules. So by using this number, we get an amount of a substance that is small enough to hold, but big enough to see. Okay? Where did that crazy number come from? It came from carbon-12 and atomic mass units. They're all related, and they are related because it was intended for it to be so. The value of the mole is the number of atoms in exactly 12 grams of pure carbon-12. And we heard about carbon-12 because we said that the atomic mass unit was 1/12 the mass of a carbon-12 atom. They are defined that way so that we have a nice relationship between grams and atomic mass units. So 12 grams of carbon is 1 mole of carbon atoms. And that's equal to 6.022 times 10 to the 23rd carbon atoms. So we've got a relationship here between number of atoms and mass of substance. So just like we can use dozen to convert between numbers of eggs and dozens of eggs, we can use the mole, Avogadro's number, to convert between number of atoms and moles of atoms. So we have this relationship, 1 mole is equal to Avogadro's number, 6.022 times 10 to the 23rd atoms. That's going to be a very useful conversion factor. We can write it this way, 1 mole of atoms over Avogadro's number of atoms, or we can put Avogadro's number on top and 1 mole on the bottom. And this is like what you would do with a dozen. So 1 dozen eggs is equal to 12 eggs, right? Or you can say 12 eggs per 1 dozen eggs, right? So if I wanted to know how many eggs are in that 5 dozen package, we could probably figure that out without writing it out, but let's just write it out. 5 dozen, we can use dimensional analysis and the relationship between dozen and number of things to calculate that. I want dozen on the bottom, and I want number of eggs on top. And there are 12 eggs in a dozen. There are not 12 dozen in 1 egg, right? We recognize that as being silly. So I have 5 times 12, that's going to be 60 eggs. We're going to use Avogadro's number in just the same way. So a pure silver ring contains 2.80 times 10 to the 22 silver atoms. How many moles of silver atoms does it contain? You know, we've got this basket with 92 eggs. How many dozen eggs are in there? It's the sort of question we're asking. So this is dimensional analysis. We're starting with a number of atoms. So we've got atoms of silver, and we're asked how many moles. The mole is a unit, and so we're going to go with moles of silver. Oh, I forgot to point out when we first talked about mole. Mole is a unit with very few letters in it, and yet it does have an abbreviation. So mole is abbreviated MOL. Don't ask me why. So if you see MOL, it's the same as MOLE. So we can go directly from atoms to moles using Avogadro's number. So we're starting out with 2.80 times 10 to the 22 atoms of silver. I have 1 arrow, so I only need 1 conversion factor. I'm going to put the units in first and then the numbers. So I want to put moles of silver on top and atoms of silver on the bottom. Now I know I need Avogadro's number. Sometimes we get confused where to put it. Mole is like dozen. Atoms are like eggs. Is it 12 dozen to 1 egg or 1 dozen to 12 eggs? It's 1 dozen to 12 eggs. So 1 is the number that goes with mole, and instead of 12, we use that crazy number, 6.022 times 10 to the 23rd. Our units are working out here, and so now we just have to do the math. You need to be able to do scientific notation on your calculator, because you cannot convert this to a decimal and plug it in. There's too many digits. So get your calculator out if you haven't already and do this with me. You can get the same answer usually in a couple of different ways. Some of the ways are better than others. Some of them are dangerous. So I want you to do this with me. There's an EE or EXP button. And any scientific calculator should have that. There are a few odd ones that'll have one that says times 10 to the X. Those tend to behave badly, but they can be used. So I'm just going to be talking about EE or EXP. Those buttons, they're just named different on different calculators. I've got a TI-36X Pro and it says EE. So this EE button is a shortcut. As you press that, think times 10 to the. So when I want to put in 2.80 times 10 to the 22, my keystrokes are going to be 2.80 EE 22. So 2.80 EE 22. I know mine only shows one E, that's okay. You don't press it twice. And then I need to divide by 6.022 times 10 to the 23rd. So I'm going to divide by 6.022 EE23 equals. And my calculator is giving me this. I should use significant figures to decide how much of that I need to keep. 3 significant figures, 4 significant figures. The beautiful thing about scientific notation, there's a trailing zero here. There's always going to be a decimal point if there's trailing zeros. So you really don't have to think too much. It's all the digits before the time sign. It's important to use proper scientific notation. Proper scientific notation has the decimal point after the first non-zero digit. We don't want to call this 28.0 times 10 to the, I have a hard time doing that in my head. It's always after the first digit. So this should have 3 significant figures, and I'll call this 0.0465 moles of silver. If you're not entering scientific notation correctly on your calculator, what happens is you divide by 6.022 and you accidentally multiply by 10 to the 23rd. So then you're off by 10 to the 46th power. It's kind of significant. If you're having trouble with your calculator, please see me during lab and I'll speak with it and get it straightened out for you. So that's great. We can convert between atoms and moles, but to count them by weighing them, we need one more thing, the mass of 1 mole of atoms. So that's called the molar mass. The molar mass is the mass of a mole. The atomic mass is the mass of an atom. Okay? So because of how the mole and the atomic mass unit and the gram are all defined, this is true. An element's molar mass in grams per mole is numerically equal to the element's atomic mass in atomic mass units. It's actually simpler than those words suggest. So here we have a mole of aluminum. That's Avogadro's number of atoms, and 1 mole weighs 26.98 grams. That number is found in the periodic table. It's under the symbol for aluminum. What is the mass of 1 aluminum atom? It's that same number, 26.98, just put a different unit on it, atomic mass unit. So this is the atomic mass. This is the molar mass, the mass of a mole. It's the same number. So we've got the atomic mass up there and the molar mass on the periodic table. A mole of carbon atoms, Avogadro's number of carbon atoms. 1 mole weighs 12.01 grams. What does 1 atom of carbon weigh? 12.01 AMUs. Helium, 1 mole of helium, Avogadro's number of helium atoms. That weighs 4.003 grams. How much does 1 helium atom weigh? On average. Same number. So if we're talking about 1 atom, we use atomic mass unit. If we're talking about a mole of atoms, then we use the unit gram. So we can use this relationship between the gram and the mole that we have on the periodic table to help us find the mass of a certain number of elements, certain number of atoms. First, let's look at converting between grams and moles. And this is a very important type of calculation. We do this all the time in chemistry. So for carbon, we just looked at this. 12.01 grams is equal to 1 mole. And so we can make that into two conversion factors. 12 grams over a mole, 1 mole over 12 grams. Let's do an example. Calculate the amount of copper in moles in a 35.8 gram pure copper sheet. So what we're doing here is we're taking grams and we're changing that into moles. The conversion factor is on the periodic table. We get the units in place. We've got 35.8 grams of copper. I'm going to have one factor, moles of copper on top and grams of copper on the bottom. So the units work out. 1 mole of copper weighs 63.546 grams. This number came from the periodic table. I find the element symbol and the number underneath it. That's what I use. That's the mass of a mole. The mass of one atom would be 63.546 atomic mass units. So 35.8 divided by 63.546. I'm getting a whole bunch of digits on my calculator. I can think about sig figs before I write the number down. This one has 3 significant figures. These numbers from the periodic table are not, these atomic masses, molar masses, are not exact. So as written, this one has 5. So my answer here should have 3 significant figures. So what I'm going to do is I'm going to keep the first 3, 5, let's start that one again, 5, 6, 3. So those are the first 3 significant figures. And then I'm going to write down 2 extras because I told you that was a good idea. And then I'm going to go back and round this. The number, the first digit I'm getting rid of is less than 5, and so I just chop it off and I'm done with it. 0.563 moles. I graded worksheet 1, and some of you have some issues with significant figures and even just with rounding numbers, and you need to get that worked out now. Okay, so pick up that worksheet and make sure you look at it. I spent a fair amount of time going through there, and I actually looked at each answer. Any questions here? So now we have everything we need to go from a mass of atoms to number of atoms, or a number of atoms to mass. And so here's the general plan. You can convert grams into moles and moles into the number of atoms. And these are our conversion factors. The molar mass of the element on the periodic table, Avogadro's number, always the same. We could also go the other way, atoms to moles to grams. So how many carbon atoms are there in a 1.3 carat diamond? Diamonds are a form of pure carbon. 1 carat is 0.20 grams. So they gave me some numbers here. Let's write them down. 1.3 carats. It's a unit of mass that jewelers use. And then this part is in parentheses, which sort of suggests to us that we might need that, but that's not our primary thing, right? So we're starting with carat, and what is it asking us to find? Atoms. So put atoms over here. If you're having any trouble at all with problems like this, write the path out first. So I've got carats, I want atoms, I have to figure out how do I get from one to the other. Well, we were just talking about atoms, and what can we convert number of atoms into? Moles. right? So if I had moles, I could convert that into atoms. But we hadn't talked about carats at all. That's why we gave you this. 1 carat is 0.20 grams. Can I convert carats into grams using that? Sure. Can I convert grams into moles? Yeah, we just learned how to do that. So there's my path. 3 arrows, 3 conversion factors. 1.3 carats times in a line, times in a line, not a line there, times in a line. It's very helpful to have this path written out because now this tells us what to do. These are the units that go in the numerators on tops of the fractions. Here I've got carat, the next one is gram. Okay. The next one is mole. And the last one is atoms. Writing the path is the hardest thing. Okay? Some of you can do that in your head. Many of you, after you get some practice, will be able to do that part in your head. But for now, you really should write it down. So I want all these units except atoms to cancel out. So I take the previous unit and I put it in the denominator. Because if I divide by carat, it'll cancel out. I need to divide by gram, so it'll cancel out. I need to divide by moles, so it'll cancel out. Put all the units in first, then put numbers in. This one was given to us. 1 carat equals 0.20 grams. So I got the carat on the bottom. 1 carat is equal to 0.20 grams. What's on the top has to be equal to what's on the bottom. So you can think of this as equality here as being like a fraction. There's the line, and I can put this on top and that on the bottom, or I can put this one on top and this side on the bottom. I can just turn it 90 degrees either way. Here I've got moles and grams. Where do we get that conversion factor? From the periodic table. Here we're talking about carbon. So we're going to find carbon on the periodic table and write down what that says underneath. 12.0108 grams is what this periodic table says. Periodic tables are going to have 4 significant figures at a minimum. Some have more. There might be a little bit of variation because as new developments are made in measuring things, they get updated a little bit. Whatever periodic table you're using, just write down all the digits. Okay? Never round this molar mass to fewer than 4 significant figures. So 1 mole is that many grams. And then how many atoms in a mole? Avogadro's number, right? And this is really hard to get onto these fractions. I almost never leave enough room. We can just slant it up like that, that's fine. There are other ways that you can solve this problem, but they generally involve more thinking, and this pattern works really well, and I figure less thinking is easier, right? 1.3 times 0.2 divided by 12.0108 times 6.022 EE 23 equals. And I'm getting a really big number. How many sig figs should it have? 2. This one has 2, that one has 2, this one has, 6? And that one has 4. So 1.3, I'm going to write down 2 extra digits. You write down 2 extras, you don't even have to worry about rounding them or anything. And then my calculator says E22. That's calculator language. I need you to translate that to math language when you write it down. So don't write down E's. That is times 10 to the 22 atoms. And then rounding that, we'll get 1.3 times 10 to the 22 atoms. Any questions?
Considering sig figs,
Mm-hmm.
we always look at the 6.022 in the atoms population. Isn't that like the exact number of atoms in the mole?
It actually is not. We sometimes think of this as, just so set in stone. It's not exactly 6.022. It's actually 6.02214, and they know a bunch of other digits, but we usually don't need to include them. So kind of what happens with sig figs is usually what limits the number of significant figures are the measurements or the information that's given to you in the problem. We don't want any of these conversion factors that we pull in to limit the number of significant figures. So we don't want to round this to 12, because then that could possibly limit our answer and cause some rounding errors as well. But yeah, as written, Avogadro's number has 4 significant figures. Now, if you are really, really hating sig figs, and there's probably a fair number of you that you're like, man, that was, what was she talking about? So here's a shortcut. It won't help you out on the significant figures questions on the exam, but it'll help you out with everything else. Usually, however many sig figs you start with here in your mass or whatever, that's how many you're going to end up with. And it's usually 3 or 4. So 3 is usually a good guess. Okay? Let's do another one. So this is an example of a problem which, if I just gave this to you on an exam, we hadn't done anything like this before, but we've done the concepts. This includes the mole concept and density concepts, and you have to put them together. And I will give you at least 1, if not 2 problems on the exam that take individual pieces and make you put them together in a way that you haven't seen before. It's called critical thinking, and it's important. So how do we do this? Read the whole question. Titanium cube contains 2.86 times 10 to the 23rd atoms. What is the edge length of the cube? The density of titanium is 4.50 grams per cubic centimeter. You read through the problem. Now let's take the numbers and write them down with their units. So the first number given, 2.86 times 10 to the 23rd atoms. And atoms of what? Titanium. So that's Ti. And we're also given another number here, 4.50 grams per cubic centimeter. It's written on one line with a slash because that's easier to type into the computer. Your mind tends to not understand that that's a fraction. So write it vertically. It's just as easy to write it vertically as horizontally when you're doing it with your little hand. So grams divided by cubic centimeters. Okay? What that does is it tells us this is a fraction, and when I look at that, I think, gosh, that kind of looks like a conversion factor, right? And no, that one doesn't, I can't use that to convert anything. It's just a number of atoms. So we wrote down what we were given. What are we trying to find? Edge length of a cube. Okay. Well, what do we know about cubes and their lengths? The sides of a cube are all the same size, right? And we should know that the volume is L, the length of the side, cubed. Length times width times height, and they're all the same, L times L times L. So L is what we're trying to find. We have an equation. This is an example of a problem where we have an equation and we're using dimensional analysis. This happens a lot. So if I want to know what L is, what do I have to find? I have to find the volume. I need the volume so I can put it in this equation. Can I get the volume out of this mess over here? Well, this has a volume in it, right? So let's see if I could get this to convert into cubic centimeters. Well, I've got atoms, and what do we know how to convert atoms into? Only one thing, moles. So I can go atoms to moles. What does this density allow me to convert? Grams and cubic centimeters. If I want cubic centimeters over here, the one right before it is going to be grams. Can I convert moles to grams? Yes. And there's the path. So we're going to use dimensional analysis to take the numbers we were given and calculate the volume of this cube, and then we'll use this geometry equation to find the length. So I have 3 arrows. I need 3 conversion factors. 2.86 times 10 to the 23rd atoms of titanium times atoms, moles, grams, cubic centimeters. Atoms, moles, grams, cubic centimeters. It's a very nice pattern. To get rid of atoms, I divide, and then I need to get rid of moles. So I divide, those cancel out, and I get rid of grams, and divide, and they cancel out. On worksheet 1, we did some unit conversions, and you showed your work, and some of you doing a great job, and others of you are a little confused. You can't cancel grams if they're both on the top. They're not going to cancel. You need one on the top and one on the bottom. All the units in, now we put in numbers. Well, this number was given to us, 4.5 grams in cubic centimeters. So 4.5 grams is equal to 1 cubic centimeter. What goes in here, moles and atoms? Yeah, 1 mole is 6.022 times 10 to the 23rd atoms. And then grams per mole. Periodic table. Yeah, 47.88. Exactly how that comes out will depend on the periodic table you're using. I've memorized a lot of the molar masses just because I use them so often, and so I will generally in lecture round molar masses to 4 significant figures, and it's okay for you to do that as well. Okay, so we got all our numbers in, all of our units in. We can do this calculation, 2.86 EE23 divided by 6.022 EE23 times 47.88 divided by 4.5 equals, and based on the numbers I was given, I should have 3 sig figs, and so I'm going to write out 3 significant figures and 2 extra digits and the unit centimeters cubed. Is this the edge length of the cube? No. This is the volume of the cube. So I do not want to round this to 3 sig figs here because that can introduce rounding errors. So that's why I want these 2 extra digits. That's enough to keep us from getting rounding errors. Now I need to use this equation. So the volume, 5.0532 cubic centimeters, is equal to the length cubed, I'm going to underline the last significant figure so I can keep track of it and not have to look at everything over again. How do I find L? I need the cube root. If I do the cube root to one side, I have to do the cube root to the other side. So it's not a square root, it's a cube root. Cube root of both sides. So calculators vary in how they do that. Mine has a button. It's a square root symbol with a little square. And so if I press 3, and then that symbol, then I can put in my 5.0532 and press equals. So this now is equal to L, which equals 1.7160. Anybody else get that number? You could check this by taking that number and cubing it to see if you get this back. What happens to these units? What's the cube root of centimeters cubed? Just centimeters. So I'm going to call this 1.72 centimeters. That's how big the cube is. Any questions?